Welcome to Investigation 3, Multiplying and Dividing Integers. There's a little note on notation that we're going to see in this unit, and it's that we're going to stop using those plus signs to refer to positive numbers. You're just going to see them like normal numbers. And then negative numbers, instead of a raised sign, there's just going to be a normal sign, and it'll look like subtraction. Sometimes you'll also see parentheses, and that's basically just to help you distinguish between the negative sign and the subtraction sign so that it's easier to read. So this is negative 5 minus negative 8. That's negative 5 minus negative 8, and this is also negative 5 minus negative 8. They mean the exact same thing. Did you know that the subtraction symbol also indicates the opposite of a number? So negative 8 is the opposite of 8. And if you subtract negative 8, it means the opposite of negative 8. Negative 8 is 8. And for multiplication, that times symbol and this dot mean the exact same thing. So you're going to use multiplication to investigate time, distance, speed, and direction when you think about multiplying and dividing integers. And you're also going to look at number patterns and develop algorithms for multiplying and dividing the numbers. Now, this is Investigation 3.1. You had your quiz on Monday, and we're going to start Investigation 3.1 on Tuesday. Excuse me. We have Monday and Tuesday off this week. Happy Rosh Hashanah! For those of you who don't know, Rosh Hashanah is a Jewish holiday and is the reason we are off from school on Monday and Tuesday. So, you're having your quiz on Wednesday, and we start 3.1 on Thursday. Introducing multiplication of integers. The math department at Everett Middle School sponsors a contest called the Number Relay. A number line measured in meters is drawn on the school field. Kind of like a football field. Each team has 5 runners. Runners 1, 3, and 5 stand at the 50-meter line. That's Pascal and Dwayne, looks like here. Runners 2 and 4 are standing at the 50-meter line. Looks like Aurelia and Tori are there at the 50-meter line. Han is in the middle. For team 1, Han starts and runs from negative 50 to 50. Wow, he went all the way from here, shoop, all the way to here. Doop. Aurelia runs back from 50 to negative 50. So Han tagged Aurelia, and then she runs back doop, and tags Dwayne. Dwayne is going to run from negative 50 to 50. Doop. He tags Tori. Tori is going to run from 50 to negative 50 again. Doop. She tags Pascal. Pascal runs from negative 50 to the finish line at 0. The team whose final runner reaches the 0 point first wins. So if Pascal and his teammates are fast enough, Pascal will be the first one to make a win for his team. Let's figure out what we're going to use this for. Well, we have to write number sentences that express our answers to the questions. Use positive numbers for the running speeds to the right. Let's draw a picture as we're doing this. Now remember, every time we start in our notebook, we're going to try doing our work on the left-hand side, and we're going to make any additional notes and extra work on the right-hand side. I'm going to do that now. And it says that we need to use positive numbers. I'm making a note. Positive numbers for things that are on the right-hand side. And negative numbers for things to the left-hand side. Running speeds. Use positive numbers for time in the future and negative numbers for time in the past. Okay, so if it's on the right-hand side of the number line, or it happens in the future, it's positive. And it's going to be a negative number if it's on the left-hand side, or if it happened in the past, before time t equals 0. Let's go back to our problem now. It's a really good idea to take notes, just like we did when we're reading the problem. That way we know how to solve it better. Each runner runs at a constant speed. That means if we looked at a graph of the runners, they're going to cover the same amount of distance over time. And their running speed like that would look like that. It wouldn't look like they're speeding up and slowing down again, speeding up, and then they stop. No. Constant speed all the time. That makes it a lot easier for us. It says Han passes the 0 point running 5 meters per second to the right. Where is he 10 seconds later? Okay, this is not too hard of a problem as long as we're able to interpret it. Let's write it down. We have problem 1. It says when he's at the 0 mark, he's running 5 meters per second. I'm going to write that number down, 5 meters per second. To the right. Where is he 10 seconds later? Well, let's interpret our units first. That means that every second, he runs 5 meters. That seems pretty fast. Well, and it says we want to find the value of where he is 10 seconds later. That means we would need to multiply by 10. So 5 times 10 equals 50. 10 seconds later, he's run 50 meters. Now, for those of you interested in how these units work, or you want to try multiplying with some unit analysis involved, you can write units like fractions. This is really 5 meters per second times 10 seconds. Seconds cancel out because you have one on the top and one on the bottom. Just like if you were reducing a fraction after multiplying it. This means you have 50 meters. But that's just a little note for those of you who are interested. We can check off number 1. Yay! All done. And try out number 2. Dwayne passes the 0 point running 4 meters per second to the right. Where is he 5 seconds later? This is number 2. And when he's at 0, he's running, how much was that? We're looking back again and taking notes. 4 meters per second to the right. 4 meters per second. I'll multiply using the parentheses notation. Times 5 seconds equals 20 meters. That means, just like in our previous problem, every second he ran 4 meters. Just like this notation. 5 seconds later, he must be going 20 meters because he goes 4 meters, then 4 more, then 4 more, then 4 more. Let's try number 3 now. Aurelia, when she's running, you know what? She's running to the left. So problems 1 and 2, they were running to the right. Both of them. But Aurelia is running to the left. If we look at our number line, that means she's running in this direction. So we're going to be using a negative number. Because remember that positive speeds are this way and negative speeds are that way. Let's write it down. To the left at 6 meters per second is going to be the same thing as negative 6 meters per second. We can multiply that times 8. 8 seconds. Now, it's really important to know that at this time, Aurelia is passing the 0 point at 6 meters per second. Because if she were at point 50, 8 seconds later, she might still be in the positive. We know that we can use a negative number because she's only running on the negative side of the number line. So if we do 6 meters per second times 8 seconds, we can carry our negative over and do 6 times 8, which is 48 meters. She's at negative 48 meters. Only 2 left to go. It says Pascal passes the 0 point running to the right at 3 meters per second. Where was he 6 seconds earlier? Remember that when something happens earlier in time, it gets a negative number multiplied onto it. It said we should do things in the past with negative numbers. Now, keep in mind that we can think about the way this is going to work in real life too. Pascal was over here. He's going to run this way, past the 0 line. Now, it told us that we want to know where he was a few seconds ago. Our answer has got to be negative, which means that when we multiply, we should have one of our numbers mean negative too. So I'm going to write down problem 4. Pascal is running at 3 meters per second. That part's positive because he's running to the right, but we want to know where he was earlier, specifically 6 seconds earlier. So that's negative 6 seconds, giving us an answer of negative 18 meters. And there's our number sentence and our answer. Let's try number 5 now. Tori passes the 0 running point to the left at 5 meters per second. Where was she 7 seconds earlier? She's running to the left, and we want to know where she was earlier. Let's see what sign our answer should have. Keep in mind that left means negative and earlier means negative. We have 2 negatives, so they should give us a positive answer. Tori passes the 0 point, running to the left at 5 meters per second. She was at 50, so a few seconds earlier, she had to be somewhere in the positive. That matches our idea that we're going to have to work with 2 negative numbers. So let's write down her initial speed in meters per second, which is 5, or in this case negative 5 because she's running to the left. And we're going to write down 7 seconds earlier as negative 7 seconds. Zoom in a little. We have negative 5 times negative 7. The negatives cancel out, giving us 35 meters. This matches what we were thinking. She goes 5 meters every second, 7 seconds earlier. We can even count that over on our number line. 1 second earlier, 2 seconds earlier, 3 seconds earlier, 4 seconds earlier, 5 seconds earlier, 6 seconds earlier, 7 seconds earlier. Now my ugly finger is at 35, which exactly matches our answer. Let's see what else we have to do. This is part B of introducing multiplication of integers. You don't have to do this on Tuesday. In fact, we're not going to look at it again until next Monday, but we may as well try it out now. We want to find the products in each group below, group 1, 2, and 3. That's question number 1. Not too hard. I'm going to start by copying it down in my workbook, or in my notebook. So I'll make a spot for B, and I'll do 1. It just says find the products. Find the products means multiply the 2 numbers together. That's not too hard. I'm going to make a spot for group 1, group 2, and group 3. That way it'll be really easy to read. In group 1, we have 3 different problems. 4 times 3 equals 12. 5.1 times 1 equals 1. And our last one, 3 times 4.5 equals, can we do this in our heads? 3 times 4 is 12, and half of 3 is 1.5. So this should be 13.5. And let's just clean up our answers a little bit by drawing a box around them. We could also try multiplying this out long way. Notice that I did 4 times 3 plus half of 3. If we multiply it out long ways, we get 4.5 times 3, which is 15. Carry the 1. 3 times 4 is 12 plus 1 is 13. And I get exactly the same answer, 13.5. Let's try group 2 now. Group 2 is a little bit different. In this set of problems, each one has a negative number. That means, since there's only one negative in the problem, we carry it over. Our answers ought to be negative also. So we have 4 times negative 3 is negative 12. Negative 12. Our next one is negative 1.5 times 2 equals, what's 1.5 times 2? Should be 5. Because 1 times 2 is 4 and half of 2 is 1. But that's negative again, because it's negative 1.5. Then we have 10 times negative 11. That should come out to a negative number again, negative 110. We can again clean it up by doing some boxes around our answers. If you find that your negative number gets covered up by the box, you can make it over again. And here we have our negative 12. Let's try group 3 now. In group 3, we have a similar set of questions, but each one has negative numbers. We have negative 4 times negative 3 equals positive 12. Remember, two negative signs cancel each other out. We have negative 7 times negative 4 equals positive 28. Again, positive, because we have two canceling each other out. And we have negative 5.2 times negative 1 equals 5.2. And it's always nice to make your answers clear. Thanks, guys. By putting boxes around them. Let's take a look at question number 2. We have to describe what the examples in each group have in common. Well, as we talked through it, we actually already did that. I'm going to write it down right below. Problem 2. Group 1. Can you guess what it is? Has all positive numbers. I'm writing it in shorthand just to make our video a little faster. Group 2 has one positive number and one negative number. Group 3 has both negative numbers. That's pretty much what they have in common if we look at their characteristics. Use your answer to part 2 to write 2 problems for each group. You had to do this back when we did investigation number 2. That's basically like where we take group 1, group 2, and group 3, and we add a couple problems for each of them. I'll do it for group 1, but I'm not going to do it for the other 2, because you know how to do that on your own. So for group 1, I could choose another set of problems that have both positive integers. I could do 4 times 5, and I could do 1 times 15. That would fit well into group 1 because they have positive, and group 1 also has positive. Let's try group 2. Group 2 is a little bit different. We talked about how there's one positive and one negative. So I could do negative 2 times 3, or I could even do negative 4 times positive 5. Group 3, they should both be negative. But we're going to go on now to problem number 4. Describe an algorithm for multiplying rational numbers. Now, an algorithm is just a set of steps. Maybe we should make that as a note. We don't want to forget what an algorithm is. Algorithm equals a set of steps or a procedure. You remember what a procedure is, right? For solving a problem. Now that we remember what an algorithm is, we have to write one. It seems like there's going to be a different algorithm for if there's one negative number and if there's two negative numbers. We can write down what to do if there's one negative number first. This is problem number 4. So going to write for one negative number, take out the negative sign, and then put it on your answer. Your answer will be negative. If you have 2 negative signs and they're next to each other when you multiply, they cancel each other out. So in that case, you can multiply normally. And your answer will be positive. We're all done writing our algorithm now. We're almost to the end. we just have 5 and 6 left. We're going to use our algorithm, our strategy, that's another synonym for algorithm, to multiply these rational numbers. Yikes! Do you remember how to multiply with fractions? We'll review it. 5a is negative 1.5 times 3/4. Zooming in, 5a, negative 1 1/2 times 3/4. The way that I like to multiply this is actually by turning them both into improper fractions. This is going to be equal to, that's negative 2/2 plus 1/2, so that's negative 3/2 times 3/4. When we multiply both numbers across. So we have negative 3 times 3. Basically, this is equal to negative 3 times 3 divided by 2 times 4. Pretty simple, which gives us negative 9 over 8. Now, we have to write it as a mixed number again. That's equal to, well, negative 8 over 8 plus negative 1 over 8, right? Because there are 9/8 there. I know that that's going to be equal to negative 1 1/8. And that's how we multiply fractions, even when we have a negative number. Notice that I didn't have to worry about my negative sign. I just could carry it over directly to the answer. Now, problem C is just like problem A, so we're not going to solve it. You can carry our negative sign over the same way. Problem B, though, we will solve together, because it shows that we can cancel out our negative signs. Problem B has us multiply negative 1/2 times, in parentheses, but remember those parentheses don't matter, negative 3/4. Now, I'm just going to cancel them out right now. Now they are positive. That gives us the same thing as 1 times 3 divided by 2 times 4, which is equal to 3 over 8. Fortunately, we don't have to reduce this one, because it's already in lowest terms. That means the number on the bottom is bigger than the number on top. Let's take a look at number 6. Is multiplication commutative? Does the order of factors matter? For example, are these multiplication sentences correct? Well, first we've got to know what commutative means. We talked about it a little bit in class, but in case you're watching this video early, I'm going to make a note on my right-hand side for our new vocabulary term, commutative. If something is commutative, that means it works in either direction. Basically says that A times B equals B times A, or A plus B equals B plus A. If addition is commutative and multiplication are commutative, that is. So we know that multiplication should be commutative if 3 times 2 equals 2 times 3. We can check our answers to each one. 3 times 2 is equal to 6. And 2 times 3 is also equal to 6. Therefore, multiplication is commutative. Now, we are going to actually discover that through solving this problem. It wants us to figure out whether the problems are correct. So, we're going to write down for part C, this is for question 6. 3 times 2 does equal 2 times 3 equals 6. Then we can try the next piece. Negative 2 times negative 3 should equal negative 3 times negative 2. Let's try it out. Negative 2 times negative 3 equals negative 3 times negative 2. Let's try it. We know that in both cases, the negative sign should cancel out because our algorithm showed us that it works in every single case. Two negative signs cancel each other out, multiply normally. So that's 6 equal to 6. This one's correct, and that one's correct. Let's try our last one together. Here we have one negative sign in each part. So we're going to do negative 2 times 3 and say that it's equal to negative 3 times 2. Check, because negative 6 is again equal to negative 6. Now, to answer it, I would want to answer all 3 questions. Is multiplication commutative? Yes. Does the order of factors matter? The order doesn't matter. Are the multiplication sentences correct? Yes. So, in order to not get confused, we're going to write our answer as the sentences are correct. Which means that the order does not matter. That's the whole meaning of commutative. Therefore, multiplication, even with negative numbers, is commutative. We have a complete answer to all 3 questions, 1, 2, and 3. Congratulations! You basically are finished with Investigation 3.1. That means if you watch this video and you did it with me, class on Tuesday and next Monday should both be a breeze. If you have any questions, please feel free to comment, ask me in class, or leave a note. Bye!